All right, today we're jumping into a real classic coding interview problem, subarray sum equals K. Now, this one it's just a fantastic test of your problem-solving skills, mainly because all the obvious answers, they're basically traps. So let's just dive right in. And that really is the key question, isn't it? We're going to start this journey by looking at the solutions that seem right on the surface. You know, the ones your gut tells you to write. But they're all secretly flawed. And we're going to see how each one of these failures actually guides us, step by step, to a truly brilliant and super efficient final answer.
Okay, first up, the challenge. Before we even think about writing code, let's make sure we're all on the exact same page about what we're trying to solve.
So here's the deal. You're handed an array of numbers and a target value. Let's call it K. Your job, your mission, is to figure out exactly how many subarrays inside that original array add up perfectly to K. And here's the most important word to remember, continuous. That means the numbers have to be right next to each other, like a block. No cherry-picking numbers from all over the place.
All right, section 2, a journey of flawed attempts. This is where the fun begins. We're going to walk through those first ideas that pop into your head and figure out exactly where they fall apart. This is how we're going to build up our intuition.
You know, the first thing a lot of people think to do is just check the easy stuff, right? And this code here, it does exactly that. It just loops through, sees if any single number equals K, and then checks if any two numbers next to each other add up to K. And look, it feels pretty reasonable. For a simple case like 1, 2, 3 with a target of 3, hey, it actually works. But there is a huge flaw hiding just under the surface. And this example just lays the problem bare. If you give this code an array of 1, 1, 1 and tell it to find a sum of 3, it's going to tell you 0. Nothing found. But the right answer is obviously 1, the whole array. Our code fails miserably because it's fundamentally blind. It can't see anything bigger than a pair of numbers.
So that's the big takeaway from our first try. The huge mistake we made was thinking in pairs, not in ranges. Okay, so how do we start thinking in ranges? Well, that brings us to our next attempt.
So our second try is a bit smarter. It brings in this idea of accumulation. Instead of just looking at pairs, it'll start at one number and then keep adding the next one and the next one, checking the running sum as it goes. This is a big step up, for sure. It can actually find those longer subarrays. But, yep, as you've probably guessed, it's still got some major problems. Yeah, there are two really sneaky but fatal flaws here. First, look at that break statement. The moment it finds one subarray that works, it just quits. It stops looking for any other possibilities that might start from the same spot. And second, there's this hidden assumption baked into the logic. It thinks all the numbers are going to be positive. The second you throw in zeros or negative numbers, this whole thing just completely falls apart.
Okay, now this is what I like to call the killer input. This is the one that just shatters everything we thought we knew. An array of 3 zeros, 0, 0, 0, and we're looking for a target sum of 0. Now, based on the code we've seen so far, what would you guess the answer is? Maybe 3 for the 3 individual zeros? The real answer is a lot stranger than that.
The correct answer is 6. 6. How on earth is that possible? Well, let's break it down. You've got the 3 single zeros, you've got 2 pairs of zeros, and you've got the whole array itself. Add them up. 3 plus 2 plus 1 is 6. All of those are continuous subarrays that sum to 0. Our simple accumulation logic just has no way of handling that level of complexity. So where do we go from here? Well, we could write a brute force solution, nested loops that literally check every single possible subarray. And hey, it would be correct. It would get the right answer for our crazy 0 example. But it is so slow. We're talking O of n squared complexity here. For any reasonably large array, it's just going to be way too inefficient. We need a fundamentally better way to think about this. Okay, section 3, the algebraic turning point. This is it. This is where we stop trying to put band-aids on broken logic, and instead, we're going to completely reframe the entire problem. The way forward isn't about adding more loops. It's about a simple, elegant piece of algebra. So think about it. For this whole journey so far, we've been stuck asking one question. Where should a subarray start? We pick a starting point, and then we check everything that could come after it. It's so inefficient because we just end up calculating the same sums again and again and again. But what if we flip that question completely on its head? This right here is the aha moment. Instead of asking where a subarray should start as we move through the array, at each new number we ask, how many subarrays that end right here at this exact spot have the sum we're looking for?
This little shift in perspective, it changes absolutely everything. Which brings us to section 4, prefix sums to the rescue. See, that new question we're asking, it unlocks an incredibly powerful tool that is just perfect for this problem, the prefix sum. So what is a prefix sum? It's really just a running total. That's it. As we go through the array, we just keep track of the sum of all the numbers from the very beginning up to wherever we are now. It's a super simple idea, but it has one very, very powerful property. And here is the magic trick. With prefix sums, the sum of any continuous subarray, say from some index I to another index j, is just the prefix sum at j minus the prefix sum right before I. All of a sudden, we can find the sum of any range in a single calculation. No more looping every single time, it's instant.
So let's just peek at the algebra for a second. We want our subarray sum, right? Which we now know is prefix of j minus prefix of I minus 1. We want that to be equal to our target k. Now, if we just do a tiny little bit of high school algebra and rearrange things, we get this beautiful equation. The old prefix sum we're looking for equals our current prefix sum minus k. And that tells us exactly what we need to find.
So here's the core logic, laid out plain and simple. As we're calculating our running total at our current spot j, all we have to do is ask one simple question. Hey, how many times in the past have I already seen a prefix sum that's equal to my current sum minus k? And every single time the answer is yes, that means we've just found another valid subarray that ends right at this spot.
And all of that, it leads us to this, the final, beautiful, optimal code. We just go through the array one single time, we keep track of our running prefix sum, and we use a hash map, or a dictionary in Python, to instantly store and look up how many times we've seen every prefix sum in the past. It's clean, it's lightning fast, and most importantly, it's correct.
Okay, last section, the optimal pattern summarized. Let's just do a quick wrap up and talk about why this whole pattern is so incredibly powerful.
I mean, this solution is just a massive win all around. It only touches each element once, which makes it super, super fast. It handles negative numbers and zeros like a champ, no extra if statements needed. And really, the hash map is the hero here. It gives us an instant, we're talking O of 1 way to look up our entire history of sums without ever having to scan through the array again.
And look, if you ever find yourself in a coding interview and you get this problem, this right here, this is your money sentence. It perfectly wraps up that whole logical journey, from a slow, kind of clunky solution to something that's efficient and really insightful. It shows you didn't just stumble upon an answer. You actually understand the why behind it. So, what other problems out there do you think this powerful pattern could solve?